Hello, hello. We'll get started in just a minute. Okay, and I think we're good. Okay, so welcome to USD with me. This is a live stream where I'll typically work on something USD related, developer related mostly, writing Python code to build something using USD. So previously, we created a material with full spec material with all of the textures and everything that you could do with the USD preview surface material. Um, last week, no, 2 weeks ago, I shared some of the stuff that we're doing with the USD code samples and how that repository and project is working. And I did a little bit of work there. And so today, so last week I wasn't on because it was SIGGRAPH, which was pretty great. We had a lot of OpenUSD sessions and discussions there. So it was really great to talk with other developers about what they're working on. And one of the things that was pretty common was UsdSkel, which is the rigging and animation API for characters, and mostly geared towards crowds. But uh, that's about all I can say. Hey, Nandu, welcome. Because I've known of it, I've used UsdSkel, but I haven't gotten into the innards of it and really done coding around it. So that's my goal for this week, and maybe it'll be 1 or 2 weeks after this, because it is a big topic. I wanted to get more familiar with UsdScale and how that works. So so that's what we're doing. So for today, I wanted to start from the very beginning, and that's let's open up uh, an example of UsdScale, get a feel of just how the data is laid out, try to understand what different prims and properties are doing, and then we can try to create our own little rig and animate it. So let's dive into it. I'll be using USD View today, I think. If we need to, we can jump into Omniverse as well. The cool thing and the reason I wanted to use this is we had a recent release of this 23.8. So this is the latest and greatest USD and USD View. And you can get that from the launcher now. So that's what we're gonna try it out. Make sure that I don't think anything's really changed on this front, but with the latest release, but we'll see. So I went ahead and downloaded the quintessential example, USdSkel example. If you search USdSkel example, um, there's this asset that you can download. And if you go to downloads and videos here, you can there's a little image to give you an idea of what you're downloading here. So that's what we're going to be looking at. So let's go ahead and open that. Saved it somewhere over here. And there's a couple of animations. It looks like lots and lots of stuff. So let's open up the top file and see what we're dealing with. I think we'll take this in chunks. We can study the whole thing, but for the sake of learning this, my first goal was going to be to rig a cylinder and bend a cylinder, and that would be first step, right? Let's do some weights on the different vertices and see that react, deform based off of that. Then we could try to layer on blend shapes potentially. But let's see here. So every rig will have this scale root prim type. Take a look a little bit at what kind of properties this has. It's got a skinning method, classic linear. There's some prim vars here. We can see that every property related to UsdSkel has a Skell prefix, so that's helpful. Here it's pointing to the skeleton, which would be here, and that's a skeleton prim type. And somebody's asking about this stream. Let me let them know. We're on live right now. Hi, Mom. All right. Twin Snakes is asking. So the goal here, Twin Snakes is asking, what DCC am I going to be skinning the mesh in skeleton rig? I am not going to be. I'm going to try not to do this in any DCC. The goal is to learn how to do this programmatically. So there are great connectors and exporters for exporting a character rig from iClone or Maya, and that's great, and it works. The goal here is to understand how the system as a whole works and how to author and translate this data so that you could write a translator from any application and be able to author, export, and author skeletons for USD. So yeah, so we'll be using Python. Well, the end product will be a Python script. We'll see, if for the basic cylinder example, I'm going to need a mesh. We'll see if I'll probably use Maya or something to export the mesh and save it as get the vertices and all that, so then I can refer to it programmatically. So we'll get there. Cool. So that's pointing to the skeleton prim, and that's about it there. And then we have some X forms here, which is going to be the different what we would call subassets or potentially subcomponents. Let's see. These are references, I think. If you haven't seen this, there is this little question mark that tells you what these colors mean in the outliner. And so this means that it has arcs, and it does have a reference to female full. Looks like these are all coming from the same file, but we can see here that from the full, there is a payload, and it's payloading in different subassets. So, and for the most part, these are pretty simple, right? It's the geometry, and it's the materials for each individual part. So, if you're building crowd characters, you would want to be able to, swap out shirts and pants and be able to create variety in your crowd that way. but potentially use the same rigging setup for all of them. So I think that's what they intended with this layout here. Let's see what that variant selection is here. Rig complexity. Okay. Cool. So we can see here. I think we'll have a visual change with that variant. And does it have any variant? No. Okay. And then the scale has everything else. So it has joint names, 66 joints. Lovely. And these are the paths to those joints. Why don't I see? What is the value here? I feel like that should be pointing to some parameters, but maybe not. I think in Omniverse we might actually be. Let's take a look at what Omniverse looks like. I think in Omniverse we list out these joints, but we'll see. And then bind transforms for all of those joints. If I remember correctly, bind transform is the world position of where these joints are located when you do the binding. This might be a really good example to run through. I'm just buying time as RTX is loading. There we go. Kind of want to. Does this have everything? I think it does have everything. I kind of want to look at this as an example. Seems like it'd be way easier. All right. I have lost my patience with that one. Let's do a composer with the latest Kit 105. So yeah, while we're waiting, we can talk about that. I think Ed Mars behind the scenes sharing links. But we do now have updated the NVIDIA website. Kind of want to save some of this stuff for some stuff that we have planned today and tomorrow. But this is fine. So we have, this is totally revamped. We have a lot of new content. We have our developer YouTube series here. The playlist is here, so you can watch everything here once they've been uploaded. First steps is kind of where I like to have people start. We have a new learning path for USD developers, and we'll look at that in a moment. Instructions on how to get USD, whether it's from the repository or USD core. Some explanations about how to look up code. So we now have the start of Python API documentation. So we could come in here, UsdSkel, and take a look at some of these things. It's ordered by class and methods. So we can look at that skeleton class. And this is using the documentation from C++, but trying to kind of massage it into something that Python developers would like to read. So it's a work in progress, but pretty great start here. So you don't have to go looking at C++ code all the time. So we have that now, and places to get help: our Discord server, our Omniverse forums, the AOUSD forum. If you missed that announcement, there's now the Alliance for OpenUSD, which is going to be working on defining the standard that is OpenUSD, so that we can share this effectively across different applications and platforms. And there's lots of very helpful developers here where you can ask questions and get some answers. And then the Academy Software Foundation Slack, which is also very helpful. And then as far as learning path, there's good learning content out there. I think what there hasn't been until now is getting from point A to point B. Where do I start? What order do I learn these things? So that's what the goal of this learning path is telling you, hey, look, great place to start is our USD DLI. It's free, and it covers lots of different things about USD development. Then we have the optional Essentials of USD and Omniverse, which is another DLI course. And then some tutorials, making your first stage, defining your first prims, and properties and traversing stages. So some of these are, the Pixar tutorials that we know and love, and just trying to give you the best step forward, take the best steps forward, so you don't go into a rabbit hole where you may get lost. So this is the first learning path of hopefully many more, and each learning path will have clear description of what you're learning, what the learning objectives are, so that before you go committing these 90 minutes, you know what you'll learn out of it. And then organizing all of our learning content, where to find it, where is it, categorizing them as written tutorials versus video tutorials and all that. And then in the independent learning, we have a brand new white paper on principles of scalable asset structures. So that I still have to digest, but there's a lot of information about just kind of generically, abstractly describing how some best practices for asset structure so that we can apply this to different industries because the examples that we've had until now have been media entertainment focused um, and we need to be able to explain this for a variety of industries, and maybe there will be some deviation between industries, but for the most part, um, these are the things that we found that are common to all industries and things to take into consideration for everyone that's building an asset structure for their company or wherever that might be. So we have that, and I don't want to spend too much more time on this. And then our code samples are finally out, updated with the new code snippet style, and also the repository is available so that you can contribute. So we'll talk more about that for sure later this week and in the future. But that bought me more than enough time to go ahead and look at this in here. Okay, so we do have payloads here. Here's our Skell. And in Omniverse, this is what was tripping me up, is that we do kind of show the hierarchy of the bones using these omni joints, which is a custom schema for joints here in Omniverse only. But it is, as you can see, it looks like this is something that I'm not totally familiar with, but I think we built this on the fly because obviously the Pixar example has no notion of omni joints in it. There's nothing authored about omni joints. We saw that from here, right? All it defined were the joint names and joints as properties in the vanilla USD schema way. So we will need to explore this further in the future, but we do want to keep things fairly vanilla right now. Cool. And there's no animation on this one. So if it looks like these are intended to be opened. These are separate stages here. If we open, for example, the walk one, and take a look to see what's going on here. So she is in a walk pose. These lights look terrible. She looks so dark in this. I don't know if I have control over brightness of that light. All right, but it's a little better. So if we play this back, we should get a walk cycle. Sweet. So let's take a look at what this is. So again, the same female group and a Skell anim. If we look at the composition here, we have the root is the walk USD, which is referencing human female. I'm going to go ahead and open up this here. Yeah, so it's referencing that one that we opened before. And then we have the full geometric LOD. Let's see what that looks like with the other LODs. Yeah, look at that. And these all the rig will work for all of these, right? So that's pretty great for being able to swap out lower lower LODs when you need the performance, especially if these are crowds, right? You may have thousands, hundreds of thousands of these, and you want to make sure that you can swap to lower LODs where you don't need it. So that may be fun to explore a bit. And I think that's it in this composition. This is just going to be there's a variant selection under there. Okay. And it looks like this variant brings in a different reference so that we can actually preview that. So you saw that it was full.usd. If I switch this to low, we get the low USD reference. So that's how that's working there. All right. And then the thing that was added was this scale animation. So all this looks to be doing, and this is me trying to decipher just from the composition stack here, but this is the root, and then this is a reference, and because this doesn't have any sort of arc on it, this must be defined in the walk USD file. So they referenced the character, added the animation, and this is a new full stage. So that's interesting there. We can go ahead and open up. This might be in binary. Nope, USDA, perfect. Looks like it has time samples on the extent, which is good practice. So we have valid bounding boxes at every frame as the character is animated. What else did they author in this one? Here's the animation. It authored an animation source, right? So it said in this walk USD, it set a property for the human female group to target the scale animation that we want. And it's also moving the character. So the root transform of the character is authored here. So that's interesting. And then, and this is the skeleton, right? Should be. Group is the skeletal root. Okay. And then here's the scale animation that's only defined in this file. And it's got some blend shape names here. It's got some weights on. I guess it's just one weight at 101. And then here we're animating the joints. Rotation, scale, and translate. Easy peasy. The one thing that I want to check is it looks like these are redefined here, right? We said there's there were 66 joints in here. Where was I looking? Oh, it'd be on the skeleton. 66 joints here, but on the scale anim, there are 109. And maybe that's because of blend shapes? So that's something to look into. Cool. So things to research here. But for the most part, they look similar. Yeah, I'm not sure what the difference is here without looking more closely. All right, we'll come back to that. I'm sure actually a lot of times you can look here and it'll tell you what the schema itself has a documentation about every property. So let's start with skeleton. So this one, so when you click on a property, it'll show the metadata for that property. And this one says it's an array of path tokens identifying set of joints that make up the skeleton and their order. Okay, so parent-child relationships are defined by the paths, right? Um, so very simply, torso is parented to hips because it's hips/torso. And it's not required that the name at the end of each path be unique. Yeah, that's basic SDF path definition. The path, each path has to be unique, but you can repeat names in the path, right? So you could have just a foot and foot, but as long as they're parented under some sort of right and left hierarchy, that would be acceptable. And then Skeletal. Okay, so this is the joint that the animation applies to. So potentially we have duplication of joints in here. And I feel like maybe this one didn't have cheeks. Yeah, see, so this one didn't have cheeks defined. So this must be drivers for the blend shapes too. Left cheek, right cheek, that kind of thing. And take a look to see how that relates to the blend shapes. All right, we got to read the manual. Okay, so that gives me fairly good idea of how this is all pieced together. It probably would be good to start with this example instead of the big character. This is a really good tutorial. So this is the kind of stuff that I'm talking about with the learning path, is that how would you even know to look here for a tutorial? Okay, we're going to save this. File new, save as. We can put this in our assets. And we'll call this ARM USDA. Cool. So if we look at this, and ARM USDA, looks like it opened without errors. Okay, they did a rectangular prism for the arm. And I don't think is there animation on this? Nah. Well, there is a scale anim, but there's only one frame for all of these. So I kind of want to see some animation before I start picking this apart. Scale root, defining the skeleton, bind transforms. Yeah, so they only have, well, no, there should be a rotation at frame 10. Didn't do it. Was there an error when this opened? So in order, unfortunately, I don't think that's not gonna show any errors there. Unfortunately, I can't see errors here when I launch it from the launcher. I guess I could look at, I think we have a log file for that, but what I can do is if I come here, go to settings, open up the folder for the version that I'm using, and then I can go to scripts, open this folder in a terminal, and then say USD view GUI batch. It's going to launch it, but I'll have the terminal available to see what happened when this opened. So just to make sure there aren't any errors here. No, looks happy. So, but when I looked at the animation, I didn't see 2 frames. I only see one on rotation, and I don't remember what italicized values mean. It's inherited. Let's take a look at the USDA. So there isn't an inherits on here, I don't think. Oh, I see. So no, I was looking at this wrong. So it is an array of one tuple, but the value that value isn't going to show. There we go. So there's the starting value at 1. There's the ending value. It should be interpolating. It is set to linear. So I'm not sure what happened there. Let's open it in Omniverse just to confirm in another viewer. A tiny little arm. And so our timeline. That's working. Interesting. Well, at least we got the animation. I'll need to potentially report that as a bug. Let's try Storm just in case. Okay. So mystery solved. While we're here, we should be good citizens and test this in an older version. So in Omniverse, we're using 2211 for our USD version. So I have 2211 here as well. So we can test on the same version of USD. See if maybe that's a regression. Maybe with USD view, or maybe with the Hydra. Yeah, I'm not sure. But let's take a look. Yep, that's working. Okay, cool. I think we might have found a bug. So we'll go ahead and report that. We'll stick with this version for now. 23.8. And we can also compare, because the character was obviously working. So why was the character animating and not this one? Okay, so I think every rigger in the world is probably cringing at this arm here. Obviously not enough resolution for that bend there, but makes it really easy to learn here. So so we have a couple ways that we could look at this. I guess we'll start here, right? So we have skeleton, anim, and the mesh. Easy peasy. We have shoulder, elbow, hand. So 3 joints. And the animation is rotating on the elbow, right? So another thing that should have helped here is the green means that it has time samples, it's animated, whereas these have the default values that have been defined for that prim. So another helpful tip there. Okay, so we're bending at the elbow. So if we look at the bind transforms for these, we have 0, 2, and 4. We're moving along the z-axis, right? Y, x, and so these should be listed in the same order. So shoulder would be at 0, 0, 0. Then elbow is 2 units out on z, and then the hand is 4 units out on z. So it does take a little bit of work here to visualize this, because in any DCC the skeleton would be defined as a bunch of nodes here, right? Nodes in the tree. But for the sake of performance, they've vectorized them as properties on this one scale prim. So that's what we're trying to look at and decipher here. The rest transforms look like the elbow and the hand are in the same position. So we'll need to look at that. This is bind versus rest. Hopefully that tutorial explains that a little bit. And then the animation source, like we said, is a relationship. You can see here that it's got the R, A for attribute, R for relationship, and it's targeting, nice little target icon. It's targeting that model scale anim. So this is what I was hoping to start with. This is fairly easy to understand. I do wonder what's the difference between joint names and joints. Okay, so this is just pretty names for the DCCs. And this might be able to help you with translating in and out of DCCs. If the paths of the joints differ from what the DCC wants or how it likes to show it, you could probably use that to reconcile those two. I think that's all we need to look at here. Everything else is pretty clear. I'm guessing rotations are only in quaternion. So you do need to keep that in mind. And these are joint local, so they take into account the parent rotations. And then the length, like we were seeing in the other example, the lengths of these arrays need to match this joints property, because you may want to animate only a subset of the joints versus all the ones that are defined on the skeleton. Okay, feel like we're learning something here. Anything else here? So just to prove out that we are kind of understanding this, should be able to move this joint too, right? So we're still only targeting the elbow, but if will that work? I don't know. Let's see what it does. Because if we rotate it, then that would also, if we move this, it would also potentially rotate the parent. So let's see what this does. So we'll leave it at its starting position, but we're going to move it up. Oops, 2 on the Y. And we don't need this anymore. Oops, and that needs to be 2. All right. So now we can reopen this stage. And let's see what it does. Yeah, look at that. So it's stretching. It's stretching that joint right there, right? That's what I was curious about. Is it gonna move the other joint to the shoulder? But no, it's actually stretching the joint. So the arm is actually squashing and stretching to meet that. that requirement. So, all right. Data juggler, welcome. What do you mean, what is that? It's clearly an arm being stretched and rotated. Kind of. I like to add the dome light just to have a little bit of ambient lighting there. Okay, so cool experiment. Let's take a look at that document to see if there's anything else that we should learn from this here. No need to get your glasses checked. It's more of a cube than an arm. I didn't notice. I forgot to check the mesh. The mesh tells us obviously the weights per vertex. My bad. So this is the mesh, and these are defined as primitive variables, prim bars, and we have the bind transformation, which is just going to be zeroed out. We'll need to find out what that is. And this is probably just basic rigging stuff that you can see why I haven't learned this stuff yet is because I don't know the rigging basics as well. And then joint indices and joint weights. Okay, so this should be fairly easy to figure out here. Let's look at the documentation for this, see if we can understand from that. Yeah, I don't know why you would want to use that, but I'm sure there's a very important reason for that. Joint indices. So this one should be fairly easy too. I think I can explain this one. So I think this is for every vertex, we're saying which joint is influencing it and by how much. Although if you wanted to have multiple joints influencing a vertex, that wouldn't be a good way to encode that. Let's take a look though. There are 10 face vertex, or 10 face vertices. Where's the points? There are 12 points. Right, 12 points and 12 joint indices. So let's actually look at what this is saying here. Okay. So I should read this out loud for those playing at home. The primvars can have either constant or vertex interpolation, but so that would be the interpolation of the skinning. But the primvar's element size determines how many joints influence each point. So right now our element size is 1, and that's why we have 1 joint per vertex. I'd be curious to see what an example of a larger element size would look like. So another thing that we can look at, joint indices. With a element size greater than 1. Yes, thank you. Somebody is paying attention here. There's an attribute called joints, and that's what joint indices is looking for. So if we look at these numbers, so I just wanted to clarify first on the number of influences per vertex, but so now we know that there for this particular rig, there's only one influence per vertex, so one joint at any given time will affect the position, the deformation of any given vertex. And these numbers are the indices in the joint array from the skeleton. So the first 4 points are all affected by number 2, right? 0, 1, 2. So by the hand. Then, come on. Then the next 4 are all affected. That would be these at the bend are all affected by the elbow. No, I'm sorry. The next 4 are all affected by the shoulder. And then the last 4 are the middle ones that are affected by the elbow, if I got that correctly. Yeah, elbow is 1. So that's what that's doing. And then the weights. So if you had, in this case, they're all 1, there's only one joint affecting a particular point, but if you had multiple joints affecting a particular point or vertex, then this is where you would say, how much influence does each joint have on that vertex? So is the point here for this elbow affected more by the elbow or by the hand or by the shoulder? And that affects its final position when those are being transformed. So let's make sure we understand here. Same story. There's an element size. So this needs to correspond by the needs to correspond with the element size of the joint indices to get the full effect there. And then we will not dig into blend shapes just yet because I need to learn more about that or be in the right mindset for that. And then yeah, the binding to the skeleton that's affecting this mesh. Is that it? Looks like it. So we've got 2 minutes. Any questions based off of what we covered today? I'm going to put this link in the chat in case you want to read over it. I think this is probably the best place to start. So next week, I think here's a rest transform. So yes, I know what that one is. Rest transform is local space rest transform of each joint, which serves as a fallback value for joints that have not been overridden by an animation. Okay. So say you bind in a T pose, you can then define rest transforms to say your rest transform is just the arms straight down. And so what that affords you is these are your default values for any animation you build after that. They're the fallback values. So it can be a bit of a cost saving there if for example, you when you get to the point of authoring the animation, if you can rely on those fallback values to not have to reauthor those values in your animations. So a little bit of a space savings. If you unspecify them, then you have to specify the complete non-sparse animation. So there is that. So, and then also maybe for blend shapes, that would probably be relevant, right? You don't want to, maybe you don't want to have to author all the blend shape information every time. And then this isn't an exact copy of a bind transform, right? If you'd have to then transform the world positions into local positions for, or local transforms for when you're authoring the rest transforms. Cool. Binding animation to skeleton, binding the skeleton with prim, we covered that. Use the scale binding API to do the binding of the mesh to the skeleton. Sounds like you can order the joints however you like for the animation. I think that's what that means. Oh, hold on. Using that ordering a value of 0 in joint indices refers to, did we have that in here? Maybe I got that wrong. No, there's no authored scale joints on the mesh, but you could define a different order for the bones here on the mesh, and then that would be reflected, and that would affect the joint indices because the values would correspond to this property instead of the one from the skeleton. And geom bind transform, let's see if I can understand what this means. It's often the case that a skinned primitive will have a transform authored using the typical. In that case, the geom bind transform is the only transform used for skinning. And yeah, I think that's just going to be over my head based off of an experience with rigging. If anybody can explain that in simpler terms, let me know. Otherwise, I'll keep researching and see what the use case is for where you'd want to have a transform for the binding versus maybe the transform that of the prims when you've kind of assembled the character. Cool. Whoa, lots of things. I missed some comments here. Are the rotations are quaternion? That looks like that's intentional and required. So you do have to convert your rotations to quaternion for that. But the GF module has has a rotation class, which is really useful for doing any of those translations from Euler to quaternion. or from transform to quaternion. Did OV fix rest transform bug? I'm not sure. I'll have to look into that. The last version you can override rest transform. Okay, I'll look into that. Actually, this person's saying that both Euler and quaternion are allowed. And I just need to read all the comments before I talk. It looks like the answer to that question about rest transforms is that the release notes do address that. So hopefully that's fixed. Let me know. We'll be back next week. So it'd be good to follow up on that. Yeah, hit me up on Discord. I got to learn this stuff, and it sounds like you're already well ahead of me. So anything you can add is welcome. Anything else? And yeah, if you have a link or about the Euler and Euler and quaternion support, I'd be curious about that. I'm gonna take a quick look here. I know we're over time. Classes. Scale. So this would be in scale animation. Yeah, I'm not sure if if you have any information on that. I don't see any explanation of how you would do Euler. You could do transforms though and use Euler there. Did I miss anything else here? Okay, we'll dig into that next week. All right, thanks everybody for coming. I hope that was useful to some of you. We'll be learning more next week for sure, and hopefully start writing some code to build this. I think that ARM example is a good one, so it'd be good to maybe the next step would be write code to recreate that ARM, just to get a feel for the API. And there's different API schemas that we need to use for this. So it'll be good to explore that and see what that entails. All right. Thanks, everyone. See you.